This is a short lecture on the Kerberos authentication system for COMP621 Web Security at North Carolina A&T State University. The puppy doesn't look friendly. He's Kerberos. In Greek mythology, he guarded the gates of Hades to keep the dead from leaving. Kerberos is an authentication protocol developed at MIT in the 1980s. They had a bunch of workstations, and the workstations had to authenticate themselves to various servers, such as file servers and print servers. Kerberos has been in use since then. The Microsoft Windows Active Directory system, among several other systems, currently use Kerberos. It relies on encryption, and you can use the symmetric or asymmetric key encryption. AES is commonly used now. Kerberos has user IDs and passwords, just like an awful lot of login systems, but the passwords are not sent from the client to the server. Instead, the passwords are used as encryption keys, possibly after some key stretching that is done by taking the key that the user enters and running it through a hash or something, and then taking the hashed bits and using that as the encryption key. There are a lot of messages sent back and forth between different server machines in Kerberos. Most of these happen automatically without the user having to take any manual intervention. In addition to application servers or APIs that the user wants to access, Kerberos requires two servers. Frequently, these two server systems are located in the same machine. The authentication server, which we'll abbreviate AS, validates the authenticity of a user, and the ticket granting server provides information that the user can send to application servers for authentication. The authentication server and ticket granting server machine can create a single point of failure for Kerberos. There are several keys used in this system. We assume that each user has a secret symmetric encryption key known only to them and the authentication server. So they know the key, and the authentication server knows that key, and hopefully nobody else. That key is created from their password, possibly by password stretching, such as creating a hash and then using that hash as the encryption key. And then there's another encryption key known only to the authentication server and the ticket granting server. This allows those two servers in the system to send messages that are encrypted and only they can decrypt them. Now, each application server has an encryption key that it knows and the ticket granting server knows. And several new keys are created along the way to create access. All the messages contain a timestamp, that is the current date and time, and the messages are only good for a certain period of time. After that time period, then the systems will reject the message. The timestamps are there to keep somebody from replaying the message, somebody from recording a message and then sending it again later to a server as if it was a real message. Because it's out of date, the server will know that it's no longer valid. Even though all the messages contain timestamps, I'm not going to show them in the diagrams I have here because they're always there and they're kind of redundant. Another value that you see frequently in these is a nonce. A nonce is just a random number. The random number is created by one user and sent to the other, and then typically encrypted, and the reply is encrypted. And that way, if it gets the same random number back, it knows that this message is fresh, that this is a response to the message I sent. Otherwise, it wouldn't have the proper nonce or random number. Okay, I'm going to have a bunch of pictures like this where we show a key on the top or a lock with a key, and inside the box is some sort of data, which means in this picture there is data encrypted with unknown key. And so we send information around that's encrypted by some key or another. Okay, the basic overview of Kerberos is a client sends a message to the authentication server saying, I want to be authenticated. And the authentication server figures out that, yes, that's really you. And then we send a message to the ticket granting server, and then the client asks the ticket granting server each time it wants to access a particular application server. we can also think of those as each different API interfaces. So every time a client wants to access a different server, it asks the ticket granting server for permission, and it will give it the ticket that allows it to get access. Okay, so to start, the client sends its user ID and a nonce, we'll call this nonce1 because other nonces will appear in this system, and nonce1 to the authentication server. Everything is sent in plain text. There's no encryption at this phase. And then the the authentication server replies to the client with a message that has the user ID in it, returning that in plain text, along with two encrypted portions. One part, which is the user ID and a newly generated key, is encrypted with the key that's shared between the authentication server and the ticket granting server. Another part has the same new key and the nonce encrypted with the user's key. This is the key that the authentication server and the user share. And so this allows the user to decrypt that box and get the new key and the nonce. It will check and see if the nonce is the same one that it sent to the authentication server earlier. If it is, it knows it's the right reply, because only the authentication server could have encrypted with the key that's secret between the client and the authentication server. It saves that other part of the message, the encrypted key and the user ID, that's encrypted with the key with the authentication server and the ticket granting server. The user cannot decrypt this, but it's going to send that later onto the ticket granting server. Yes, the next step is that client will send that encrypted message that it got from the authentication server that it cannot decrypt, the one that's encrypted with the authentication server key that it shares with the ticket granting server, and sends that off to the ticket granting server, along with the name of the application server it would like to access, a second nonce, and its user ID. The user ID that it sends in plain text and the user ID that is encrypted with the key between the authentication server and the ticket granting server have to be the same. So it sends that to the ticket granting server. The ticket granting server then checks and sees everything's okay and that this user is allowed to access that server, and then creates another message that it sends back. And these are two parts encrypted with different keys. Using the new key, this is the key that the authentication server created to share between that client and the ticket granting server, and that's used to encrypt the application server that it wants to access. We sent that message to the ticket granting server, and it's replying with that. The second nonce, that way we know this is a fresh message. This has to be the same random number that we created and sent earlier, and it will send it back to us. If it's not the same, we know this is a replay attack. And yet another key. This encryption key is going to be used for accessing the application server. Included in this message is something encrypted with the key that the application server and the ticket granting server share. In other words, each application server shares a different key with the ticket granting server. The ticket granting server then, using the appropriate key for that server, encrypts the new key that it created and sent to the user and puts the user ID in there and gives this to the client. So now the client has this information. It can't decrypt itself, but it can save, because it will then send that information off to the application server to get access. So it sends its user ID, a third nonce, yet a third random number, and the information it got from the ticket granting server that's encrypted with the key shared by the ticket granting server and the application server, which includes the second key that was generated and the user ID. The application server checks the user ID in the encrypted message because it can decrypt it, and the one sent in plain text to see that they match, and now has that new key that now the client knows and the application server knows. And so now the application sends a reply back to the client with that third random number, the nonce 3, encrypted with the key that it's going to share between the client and the application server. After this, they use that second key for all the communications. So everything they send between the two servers, or between the server and the client, is encrypted with new key 2. And again, only the client and the application server know that key. Kerberos has been around for about 30 years and it's still considered to be secure. One of the potential shortcomings is that all the computers have to have synchronized clocks for the timestamps to be valid. In other words, if one computer's clock gets to be a few minutes off from the other computer, then the timestamps will be considered late even if they're not. This is unlikely considered most of these computers these days have time servers that they frequently update. Kerberos is much more secure than sending a username and password to the server. Yeah, but bad passwords are still bad passwords.